Once again, my name is Philip. I'm team lead at R&D department here in Riga. And together with Uldis, we will show you, first of all, our ultrasound machine. Yeah, so we can go inside the tent. Actually, these tents were developed when COVID started, and this is a tent which can be assembled during 24 hours, and you can do a lot of COVID testing here. But currently, we use this middle part for some demo runs. So this is the machine for ultrasound. All this, how should we show it? It basically consists of two modules. This is the patient part. So the patient is lying here, and the operator of the machine currently is at that side of the tent, but it can be basically anywhere in the world where there is a connection. Yes, so the operator has this pointing tool, let's say, and here you can see that, well, arm is moving according to what operator is doing. And this can help in situations, for example, when we want to help someone in the rural, diagnose someone in the rural area, or just like there is a reason why remote sensing would be needed.
Some pictures transfer from one side to another.
Okay, maybe I can well, move it from this side. So from here I see all this. Oops. Yes. So you can look at different angles. Can move it around. So go up, go down, like all kinds of motion. But I'm not a medical doctor, so I'm not sure that I'm doing it exactly. Yeah, so I'm not sure if our mic is working on that side. So now this was saying that this can also be operated with people who are near the patient. So, for example, you have less experienced doctor or maybe nurse who can position this tool to the part of the body which has to be tested, and then already doctor remotely can do all the complex analysis parts. Yep. So this is the first equipment we wanted to show. This is a bit like a standalone. It's purely for point of care medical treatment. And now I will show you what other things we're doing. And you can follow me here. So talking about sequencing, first, we have to extract DNA or RNA, depends on what we want to sequence. And our extraction room is located here. So you will see room is ventilated, so it's the positive pressure. And yeah, our cameraman will also take this one. So it is your, whoa, I'm not sure how to use this hand, so hope the picture is good. Okay, so these are our two machines that we use for extraction. This machine is used for sample transfer. So basically what it does, it has a sample tube with a sample inside. It can be saliva, blood, stool, you name it, depends on what's your application. We're suspended in buffer. Then this machine takes the tube, opens it, scans barcode. Then we have tips, which are then aspirating liquid, and then it is transferred to the plate. So basically, this is, you can say, simple sample transfer. So it equals to me opening the tube, taking pipette, aspirating, and putting it liquid inside the plate. But imagine when you need to process 100 samples per day, this is quite repetitive work. You can make a mistake there. Also, you need quite a lot of people to process big amount of samples. Machine doesn't get bored, machine doesn't get tired, and does it really well. So I can show you how it works. Here is our software that's controlling this robot. Basically, 1 second, I will set up a new trial run. Now tubes are empty, but it happens exactly the same time when they are not. So we just select, we say we have 2 tubes here. Then we also select tips that we want to use. For example, we say that these tips are available. So this black tip here. And then we just say to which position in plate sample should be transferred. Okay, I will turn off lights so you see better what's happening inside. Oh, I turned off everything. Okay, okay, let's start then with other machine. With this one, I pressed the wrong button, but that's not a problem. I will show you. Yeah, I will show you how the samples are transferred to the plate later. But first, I will show you this. So we have some water in the plate, and let's imagine that this was buffer transferred by our first machine. Then we just start our run. And this is basically a pipetting robot, which I will turn off the light now in the correct way. Yes, so this is what I wanted to do. So now you see, it can load tips. Now it will aspirate some liquid, just water, and transfer it to the target plate. Now it is simple sample transfer, but we also can have like a complex workflows when we're adding different reagents. We can also have different functions embedded in this machine. So this current machine doesn't have any PCR block, but we can also assemble PCR block here. I will show you this type of machine later. And you can run different workflows. For example, like DNA extraction, well, what we do in this room. So we have scripts that are doing DNA extraction. I will just pause this workflow now. Yes, so so if we have time, I will just turn on the run so that I can show you how this machine works. But talking about this machine, we have various protocols that we could use. So as I mentioned, one is DNA extraction, RNA extraction, library preparation, different kinds of extraction. For example, here we're working a lot with stool samples. So stool gut microbiota extraction, the DNA extraction. Also, we did some high molecular DNA extraction from some animal tissues. So that's the range of application is quite big. Let's see if the machine is starting. So you can see that in this lab we also have laminar flow because we want to have a safe biological environment. So it's a biosafety cabinet, and then we also have Lysis Machine because, for example, for stool DNA extraction, we need a vigorous bead beating. So this is machine. We can put plates here with our material from where we want to extract. Then we cover plates, and basically what this machine does, it is vigorously shaking the plate, and there are some beads inside which are breaking our cells. So this is important for microbiota because gram-positive cells are very hard to lyse, and we need to have this very harsh condition. Okay, just give me 1 minute. I will set up everything. So I mentioned that this machine also has option of scanning barcodes, which is important when you have a big amount of samples. So it can easily track what exactly was happening at which point. Now machine will need some minutes to boot. It's just checking if everything is okay with the position and with different robot parts. Also, different type of tubes can be assembled. So now we have like a medium-sized tube. We have solutions where we can have very small tubes, like 2 ml tubes. Also 10 ml tubes, which are much bigger. It just depends a lot on the application that you're looking for. What else I can tell about this lab? Yeah, so I guess now we just wait a bit. It will initialize soon. So this machine was actually also, these two machines, this TP7000, which you're looking at, and the one that I showed before, the TP160, they are used also for COVID testing, so for COVID sample transfer, and then for RNA extraction from the virus. And actually in Latvia also, some of the test providers are using them, and which helped us at some point to increase testing capacity in our country quite significantly. Okay, it should be ready soon. Okay. So again, I set everything up. So it remembers your last run, so it's quite easy to just continue. And then we just start, and now pay attention because it will be moving really quick. So here sample is taken. First one, then second one. There at the left side, the cap will be taken out. You will see that it will not have cap now. Tips are taking at the right side. I feel like football commentator. Then the liquid is aspirated, and then we just transfer it to the plate. It's a simple operation, but when you have a very big number of samples, it really takes a lot of effort to do everything properly. And for 96 samples, it takes approximately 20 minutes for transfer. So in 20 minutes, you have one full plate, which you can then just take and use for extraction, as I showed here. Well, of course, sometimes some additional steps are needed, but your sample is in the plate, and now you're working not in the tubes. If you would be doing, for example, manually, or still in the plate, you could do it manually, but then in general, it becomes much faster. And just to have a feeling how it would look like, I can show you some examples of, you can show the screen, just some example of extractions. So we have different plates with different buffers. We have specific tips, which will be used for specific steps. And then we have our workflow with, let's say, consecutive mixing of reagents, removing supernatants, washing, cleaning, and so on. Yes, this particular machine has only 2 magnetic racks to remove magnetic beads during purification, shaker, and heating block. We also can upgrade machine to have a PCR block, and I will show you where it is used now. So let's imagine we extracted our DNA, and then we are ready to get to the next step of sequencing. But actually, before sequencing, we have to process DNA in a specific way. We are extracting genomic DNA, and we then transfer it to the library preparation step. During library preparation, our DNA is fragmented by enzymes. We are selecting DNA of a particular size, like a side range, and then we are adding specific adapters at each side of the fragment, which will allow us then to sequence, because we cannot sequence something for which we don't know at least some small sequence. This is like a starting point for sequencing. And this starting point we are introducing artificially. So because then we know what we have to aim for. I'm describing now what is called adapters. So we're adding adapters to our DNA fragments, and then it can be processed. So this is our room where we're making libraries. Yeah. Be careful, durable. Yeah, it's quite loud. Okay, so this is a lab where we are working, and this is machine that you have seen before, but this is a different configuration. You can notice here the big block. This is a PCR block. For some steps of library prep, we need to use PCR. Also, we have different heat block position, different magnetic rack position. And then after this process, which takes actually quite a long time, approximately 5 hours, we get a full plate of 96 samples, which we then have to process a bit more. I will not dive into too many details, but basically here we're getting double-strand DNA. And after double-strand DNA, we have to circularize it. And this is needed because of our technology that we're using, which is called DNA nanoball, DNB sequencing. So the idea is that you circularize every of your fragments, and then you have a specific rolling cycle amplification enzymatic reaction, which generates a very long DNA fragment, which has a repetitive sequencing inside of it, which are equal to your starting sequence, your starting fragment. And then this DNA is being compacted into a nanoball. We call it nanoball, like a small ball of the wired DNA. And this is what we can work with. This is what we're actually sequencing. We put those nanoballs on specific chips, and then these chips are put inside the sequencer. And then with our reagents, we are able to sequence the samples. Hi, Valeria. So as Rolando mentioned, we have our frequently used, let's say, most popular sequencer G400. Here, I can show you also some parts of it. We have chip, sequencing chip. Yeah, I will show you this inside, which we locate here. Now it's just washing before sequencing. I'm not sure if you see it on the screen. There is inside a chip, and basically our DNA is now inside. Let's pretend that it is inside. we have our sequencing cartridge with all the, oh no, I cannot take it out now. So with all the reagents in the different compartments, you don't have to premix much. Basically, almost everything is premixed, and then sequencing is happening. So these machines, we can load two chips. Yeah. So this is a sequencing chip. We can load 2 chips on one machine. You see it has 4 different lanes. So one chip, I think, yeah, you would be able to run approximately 4 human genomes to have a 30x coverage. You can run 2 chips in parallel, which gives you 8 human genomes per one run. One run will take approximately 2.5–3 days. So this is not our smallest, let's say medium-sized machine. So behind you, there is a bigger machine, T7, and it already has different, well, obviously different size and also different throughput. So in one run, if you use it to full capacity, it can give you approximately 64 human genomes, and it runs a bit faster, actually, approximately 2.5 days, I think. So this is our big sequencer. And let's now see the biggest sequencer in the world, which we call Titan. We also have it here, and not actually in many places in the world it is available now. Okay. So here in Latvia, we're lucky to have it. And it can give us approximately 640, so 10 times more than T7. And T7 is already a very powerful machine. So 10 times more powerful machine, 640 human genomes per, I think it takes a bit longer time, it's closer to 4 days. So here it is. So the big blocks are imaging cameras. Maybe we can, yeah, have a look inside. Maybe I can take it. I will show you. So the idea here is a bit different. It's an open space. You can, when it's working, you can see that how chips are moving. So basically, there are different liquid tanks there, to which chip is immersed. And then the reaction is imaged in one of these 4 things. Yes, so I think this is more or less it for our basic information. So if you have any questions, I will be happy to answer them. So are there any questions?